Hi everyone, this is Ajay here. Today I am going to discuss about orthogonal frequency division multiplexing. Right? Orthogonal frequency division multiplexing systems. As you know that the orthogonal, meaning of the orthogonality is that uh, uh, the phase difference between two signals. If we have two signals, f1t and f2t, if your the phase difference will be 90 degree. So these two signal is called as this two signal is called as they are orthogonal to each other, right? So the phase difference between two signals which maintain the 90 degree, that means these two signal is said to be orthogonal, right? As you know that the frequency division multiplexing, that means the name that we have, the frequency division multiplexing. As you know that the multiplexing is nothing but a multiple number of the transmission of the multiple number of the signals to a single channels after modulations called as multiplexings, right? And what about the frequency division? The signals that has a huge amount of the band. After dividing those frequency and modulate with different number of subcarriers and transmit through a single channel called as the frequency division multiplexing. If those signals are orthogonal, if those, if suppose we are considering two samples of that particular frequency division multiplexing signals, is orthogonal, called as orthogonal frequency division multiplexing systems, right? So this is all about some brief discussion of this frequency orthogonal frequency division multiplexing. So OFDM is called as some extension, you know about that, some extension of this frequency division multiplexing FDMA, OFDM. OFDM is the extension. OFDM is the extension of FDM. That means FDM. Before that, it was after extension of FDM, we will get the OFDM. That means the frequency that we are going to modulate in OFDM, FDM, there is no orthogonality between them. If in this OFDM system, the signals, the carrier frequency that we are going to modulate with the input signals, that signals or that signals, they are orthogonal to each other. That is the meaning of that. And what is the advantage and disadvantage of this due to orthogonality of sub case? I'll talk about later. So, right. So here we go some introduction of the orthogonal OFDM system. You know that we are just going to introduce what is the OFDM. Orthogonal frequency division multiplexing stand for, OFDM is stand for orthogonal frequency division multiplexing, is nothing but a multi-carrier modulation techniques. You know, FDM is also called as FDM is also called as multi-carrier modulation techniques, but the carrier we are just taking into consideration in OFDM, they are mutually orthogonal to each other over a given period of time, right? The beauty of the OFDM system is that only just we have a little bit difference between from the FDM. The carrier we are just taking into consideration is just equal to, just they are mutually orthogonal to each other. That is the beauty of the OFDM. What is the beauty of the OFDM system after doing the orthogonality? I'll talk about next slide. Right. So you can say that this high data rate, that means the signal we are just going to modulate. We are just going to send it, just divided, just split it, just split a lower data streams. That means this high data rate streams just divided in lower data. Total total band of these signals is just divided into a lower data bands that contains a lower data, right? And those uh, those streams just converted into parallel, then modulate with different number of orthogonal subareas, right? So as as we know that with the use of the fast Fourier transform and inverse fast Fourier transform that has been used in the transmitter, this is the this was FFT, the fast Fourier transform has been used in the receiver side, and the inverse fast Fourier transform that has been used in the transmitter side in OFDM, the conventional OFDM block diagram, conventional OFDM systems, because of it is a fast algorithm due to because of it is a fast algorithm to evaluate the performance of the system, right? So after using of the fast Fourier transform and inverse fast Fourier transform in the receiver and transmitter side, because it evaluates the fast. So this system implementation, if as far as implementation complexity is concerned, this system is a very low if you are comparing the single carrier system, right? Due to the fast Fourier transform and inverse fast Fourier transform, the implementation complexity is very low as compared to single carrier system, right? Now, now we are just going to discuss about some advantage of the OFDM. As we know that the carrier, we are just the carrier, they are spaced, they are closely spaced because of the orthogonality, and due to the orthogonality of the subcarriers, if the input signal we just modulated with these orthogonal subcarriers, so that and this system provide a high spectral efficiency because it's a spectral that we are getting, right? You suppose we have a signals that the first carrier frequency that we are just after modulating, we are just considering, we are just observing the frequency versus amplitude. That means we are just observing the frequency spectrum. Uh, the first carrier frequency we are just taking f naught. F naught is the first carrier frequency, and then after first modulation, this one is the S1D. Suppose we have S1D just modulated with the frequency F naught, we will get, because of this system is known as descent modulation. After modulation of the F naught, we will get a sync functions, right? A sync functions, and with this at this stage F naught, the first carrier frequency, and next carrier frequency will be something like that. Next carrier frequency something like that, and approximate third, fourth, something like that. Due to the orthogonality of the subcarriers, that means the frequency that we are going to modulate, they are suppose Fk. Fk is the first. Fk is the kth subcarriers, and Kf naught, K delta F, or we can say that, if you're considering value of k is equal to 2 to 0 to, where this delta F is nothing but the frequency is passing between subcarriers. That suppose we have a frequency, carrier frequency F naught, F1, F2, and so on. The spacing. These are the spacing delta called as delta F. These are the delta F, the carrier spacing, the frequency of the carrier spacing. If you are taking this the kth subcarriers, we will have a relationship between the k delta s, right? So as due to the autonomy of the subcarriers, this if you are you know observing, if you are visualizing the frequency spectrum, we will get a closely spaced overlapping the signals that we have, so that we can see the channel bandwidth. If this not happen, if there is no relation between the carrier frequency, so it may be this second after modulation, the second spectrum may be uh, something like that. It would be something like that. The second carrier frequency, it would be something like that, and the third may be over here. So there is no relation between the carrier frequency. So that's why, due to the overlapping, due to the orthogonality of the subcarriers, we will get the oval closely spaced overlapping spectrum. We will get after modulation. So due to which this system is known to have a high spectral efficiency, and if system have high spectral efficiency, it can be utilized better bandwidth, and is also capable to handle intersymbol interference because the use of the guard band. Guard band, guard band we will use between OFDM symbols in order to reduce the intersymbol interference. As I said in the previous slide, with the use of I50 and F50 block in the transmitter and the receiver side, this system is known to have a lower implementation complexity. And above advantage that we have, advantage that we have, uh, so we can say that this system is a high data rate communication system because of this above features of the OFDM system, right? So OFDM have some technology, OFDM based some technology that we have. First is Wi-Fi wireless standard, wireless fidelity. You know about that? What is the full form of this one? Wi-Fi is a wireless fidelity. It has some standards, that means IEEE 802.11a, IEEE 802.11g, IEEE 802.11, and IEEE 802.11c. These are the Wi-Fi standards which contains a very high data rate, right? As you know that how can distinguish the standards? These standards can be distinguished by the operating frequency. These standards can operate in different frequency, and these standards can be operate in other, and some little bit difference is also there. This IEEE 802.11 AC contains a high data rate as compared to this IEEE 802.11. So this is some standards which is updated. This one is the latest. This one is the outdated. So this the Wi-Fi standards which is based on OFDM technology, right? So WiMAX is also based on OFDM. Wireless interoperability for microwave access. This is the full form of the WiMAX, which includes the IEEE 802.16. These are the standards that also have a high data rate communication system, in which the number of subcarriers that we are going to modulate in this technology, that is 256, and 16 WAM modulator will be there for modulations. Right? I'll talk about later what is the subcarriers and something like that. And two broadcasting technology that we have: digital audio broadcasting and digital video broadcasting, which is also based on OFDM, right? And last one is a very famous technology that we have: third generation partnership project, LTE and LTE Advanced. This is the famous for high data rate, right? High data, approximate 10 Mbps. It contains a very high data rate systems which almost have 100 Mbps speed, right? So this is all about some advantage of OFDM and some OFDM based technologies that we have discussed in these slides. Now, OFDM modulations. Now we are going to discuss about how the OFDM modulation will take place. How obviously this system is a digital modulation techniques. So our input signal, our the modulating signal will be a digital signal, right? Then this the digital signal just mapped with QPSK and COM modulator. This is very famous modulation techniques that have been used in OFDM. So after getting cancellation symbol after modulation, we will get a cancellation symbol x of k. The range of the length of the k is nothing but 0 to n minus 1, 0 to n minus 1, 0 to n minus 1. The length of the k is just 0 to n minus 1. Just convert it into a parallel form. We will get a parallel cancellation symbol x0, x1, xn minus 1. These are the cancellation symbol where n is the number of subcarriers or length of this x of k. Both we can say that the length of the x of k cancellation symbol, because the size must be same so that we can modulate, we can multiply with these subcarrier frequency, right? So we have a cancellation symbol, just multiply with exponential cosine functions, that is the exponential cosine functions called as the fk is called as kth subcarriers. If k is equals to 0, that means the first carrier frequency. If k is equals to 1, that means we are just taking the second carrier frequency and so on. If k is equals to n minus 1, already told about that what is the length of the k is n minus 1. So if you are considering k is equals to n minus 1, that means we are just going to modulate with fn minus 1. After just adding those signals, we will get x of t. We will get x of t. That means this signal is continuous. This signal is continuous time domain OFDM signal. Continuous time domain. This signal is called as continuous time domain OFDM signals. After adding those signals, we will get a continuous time domain OFDM signals, which is nothing but just equal to 1 upon under root k, summation of k is equal to 0 to n minus 1, x of k e to the power j 2 pi f k, right? So, as you know that, if we want to calculate the first, so this is all about if you are observing this continuous time domain OFDM signal into frequency domain, just taking the Fourier transform of this one, we will get a overlapped spectrum. Suppose at this instant, the first carrier frequency will be f0, and at this instant, after modulation, we will get this red lines spectrum, and at this instant, f1 is the second carrier frequency, and this instant, the third carrier frequency after modulations, and so on, right? So after modulation, we can say that because of the orthogonality of the subcarriers, this spectrum is, about that committed a closely overlapped signals, right? Due to orthogonality. That means orthogonality the orthogonal signals that we are going to modulate with the input signals, we have a integer multiplication to each other, right? We have a integer multiplication to each other. That means if you are considering f naught, the first carrier frequency 1 kilohertz, and is the first and second carrier frequency uh, spacing is 1 kilohertz. 1 kilohertz is also spacing between uh, spacing is also between spacing between first and second carrier frequency is 1 kilohertz. So we can calculate the Ks subcarriers K delta F. We are putting those values. First carrier is K, just K is equal to 0. We will get the first carrier frequency. If your K is equal to 1, we will get second carrier frequency and so on. Plus F naught, sorry. Plus F naught. That means the carrier frequency that we have, they are integer multiplication to each other. That means the frequency, the subcarrier, the frequency of subcarrier, they are integer multiplication to each other, right? So this is the beauty of the OFDM, right? Now some mathematical expression that we are going to discuss about that. Okay, as you know that this equation is called as continuous time domain OFDM signals. These are the exponential cosine functions with the translation symbol. Just add those signals, we will get a continuous time domain OFDM signal system. And x of k is the ks subcarriers, and f naught is the first carrier frequency, and f naught is the frequency spacing between the subcarriers uh, that we have, right? Suppose and delta ts is nothing but a simple duration, and as I already talk about the spacing, the frequency spacing between the subcarriers, right? Suppose and the length of the k is nothing but 0 to n minus 1. If you are putting those values, k is equals to 0, that means we are talking about the first carrier frequency. That means what we have the first f naught. F naught is the first carrier frequency, and if we are putting the value of k is equals to 1, we will get k delta f. Delta f is nothing but, suppose we are considering the delta f is delta f is delta f, sorry, we are just considering the delta f is what? Suppose we are considering the delta f is equals to 1k and f naught is 1k. First carrier frequency, if you put in the value of f naught is k naught is equals to 0, we will get 1k. If you are putting the value of k is equals to 1, we are going to get the second carrier frequency. That means if you put those values, you will get f2, f naught, f1, f naught is equals to f naught already we have, and f1 is 2 kilohertz, and f3 is 3 kilohertz, f4 is the 4 kilohertz, and so on. That means, as you can see that the carrier frequency that we have, they are integer multiplication to each other. That means there is some relationship between them, so that they can show the orthogonality between them, right? So we have some mathematical expression that we have discussed. Now, the very important principle that we are going to discuss, that is the orthogonality principle. For two signals to be orthogonal, the inner product over a period of time must be 0, right? For mathematically, it can be, suppose we have two signals phi k f of t and phi m f of t, and these two signals we are just observing these two signals to be orthogonal. What is the condition between them for the orthogonality? As we know that the inner product, we're just taking the inner product phi kd and phi md, and over just taking the integration over a period of time, that is using simple division, taking the period of time, we will because as we have taking the star, conjugate, because we are considering this phi mt and phi kd is what? Exponential. If two signal is exponentially, exponential, if two signal is a complex number, is complex signals, so that we have to take a second signal is a conjugate, right? So for orthogonal, right? So first we have e to the power exponential e to the power j 2 pi f of fkd, and second is the minus one, right? So as you know that, just taking the multiplication of this one and this one, we will get a conditions just like that. If k is equals to, if we have two conditions, first condition is that if these value, if k does not equal to m, if this condition will occur, then it would be 0, right? If otherwise, it would be 1. So, as already talked about, what is the orthogonality principle? If inner product, integration of the inner product of two signals will be 0 under any conditions, that means this signal is said to be orthogonal. That means this signal is, the, this signal will be 0 integration, or we can say that these signals maintain the orthogonality. These signals maintain the 90-degree phase shift to each other, right? We have only one conditions to be orthogonal, that means if k does not equal to m. So for these two signals, f p and f now p, if k does not equal to m, only one condition for that we can say that these two signals maintain the 90-degree phase, right? Now, some block, this block diagram shows, what, the conventional OFDM system model. These block shows the conventional OFDM system. That means the original. This is the implementation with the help of I50 and F50 blocks that respectively we have in the transmitter and the receiver side, and also some guard band for in order to reduce the inter-simple interference that has been used in these conventional OFDM systems, right? So, the first stage, that is the input signal, which is in the form of 1010, because it is a kind of the digital modulation. It is the OFDM is said to be digital modulation that we are going to modulate. So our input signal must be the digital signals. Then after we map with QPSK and POM modulator, we can use two digital modulation techniques at QPSK and POM modulator. We will get, after getting this mapping, we will get a transition simple x of k, right? Just these signals, this transition simple complex signal just converted into parallel form. We will get x of k, this x x x of 0 and n minus 1. This also called as the frequency domain analysis. We have these samples which is in the frequency domain. If we are taking the inverse fast Fourier transform at the output of this I50, we will get a discrete time domain where these signals that we have, because discrete time domain signals, right? This is nothing but just equal to under root 1 finite summation of k equals to 0 to n minus 1 x of k e to the power j 2 by k n divided by n, right? So this is the this is the discrete, this is the samples that we have after our IFFT blocks, right? Then these samples just converted into the serial, after serial by the serial to parallel converter. Then guard band, there are different kind of the guard band we can use in these OFDM systems, but generally the cyclic prefix additions is generally preferred to use as a guard band. How it is happening over here, I'm just going to talk about. Suppose we have a OFDM, first OFDM samples, which contains the samples that we have first OFDM and second OFDM. the guard band addition between the OFDM samples called as the cyclic prefix additions, which we have different kind of the guard band additions. Like last, how it is, how it will happen, uh, how it is used as a guard band cyclic prefix additions. Suppose 32 samples that we are going to use as a guard band. Suppose we have the number n is equals to 128. We are getting, that means this number of sub carriers that we are going to modulate. I meant to say that these samples, length of these samples is 128. That means the last samples is just 120, 127, and first one is the 0. Similarly, this one 0, and the last one is the 127. That means last 32 samples we are just copied and paste is the front of this one. 32 samples that we have used as a guard band, uh, as a guard band before this OFDM samples, that will last 32. 27, I have approximate 95 and 96. I'll get it 95 samples. From the 95 samples on 127 samples, we will just copy it and paste it at the front of this OFDM samples. So total samples, the first OFDM in the first OFDM samples, how many samples will be there? That means 128, 230, 128 plus 32. How much? 160. 160 total. The samples will be 126. And similarly, in the second OFDM sample, just copied 32 samples, just paste it at the front of this first, second samples of OFDM, right? So this is the way we can use as a guard band. That is the meaning of the cyclic prefix additions. So this is all about the cyclic prefix additions. Now, this after addition of the cyclic prefix, now it's time to transmit the signals to the channels in OFDM channels. Uh, the channels can be AWG, and if you're talking about AW, if you're talking about AW, if you're talking about AWGN, additive wise Gaussian nice is a ideal channel. That means there is no practical application. That means this in this system just adding a noise, and there is no obstacles, there is no fault law or something like that that will happen. It is just ideal case. We are just considering, we can consider. And second channel can be relay fading channels, which is practical, which is practical channels that also can be used in the channel for practical observations. So three channels can be used in OFDM system: AWGN and relay fading channels and rechain fading channels. So up to right. So now the receiver blocks that we have: the cyclic prefix removal, serial to parallel converter, FFT, parallel to serial converter, and mapper demodulation process that will occur in this last blocks, and we will get output what we have sent in the input 10 something 11. It can be there's some little bit bit error because of the noise and something like that. So all the receiver blocks that we have mentioned is just the inverse process of the transmitting the blocks. That is already, we have already discussed about that, right? And now everything have some advantage and disadvantage as well. So if you're talking about the OFDM, in spite of having there's so many advantages of the OFDM, but it has two major concerns. First is the high PAPR. The PAPR, the peak power divided by the peak power. PAPR can be defined as peak power divided by the average power, right? And second problem is the synchronization. I'll talk about briefly what is the PAPR and how the effect and what is the impact on the system performance due to the high PAPR. We'll talk about the next slide, right? And second one is the synchronization. As you know that if you're talking about the previous slides, in the previous slide we have I50 and I50 block, and output of this I50 block we will get some samples, right? Uh, we will get some samples, and it is not necessary. It is, and also we have using the in this OFDM system FFT blocks. It is not necessary to get this the samples that output of this I50. It would be same as the FFT, because at the receiver side, if you are taking the samples that output of the I50, and it will be same as the FFT block as well. And but in the system, it is not necessary to get same samples that we have in the I50 at this FFT blocks, right? So some little bit is in some problems that is called as synchronization problems, frequency offset and time offset. These problems that occur in OFDM systems. So right. So second major issues is what the synchronization, right? Now because of these issue, because these two issue appearing in the form of, it can be degrade the performance or bit error performance or inter-symbol interference. One symbol interfere with another symbol called as inter-symbol interference, so that if this interference occurs, so there is distortion, signal will be distorted, and some degradation in the bit error performance as well, right? Because of these issue appearing in the OFDM system, right? So now I am going to define what is the PAPR, right? PAPR is nothing but peak instantaneous power and just divide by the average power, right? It can be for conventional OFDM system, as already talked about what is the conventional OFDM. These are the conventional OFDM systems. For conventional OFDM system, the PAPR can be PAPR just directly proportional to the number of subcarriers, the maximum. We are just considering the maximum number of maximum PAPR. Just if you're taking the logarithmic, if you're taking the logarithmic value of this maximum PAPR, it's all I just put it directly these values. It's a huge amount of it's a huge actually. We have to take the time for uh, to solve this the value of the maximum PAPR, and I'm just putting it those values. The maximum PAPR of the conventional OFDM system is just directly proportional to the number of subcarriers. Where n is the number of subcarriers. If we keep increasing the number of subcarriers, PAPR is also increases. As you can see here, the graph, I can tell you what is happening over here. You know about that these blocks for different PAPR, different number of subcarriers, we will get the different PAPR. As taking the reference is 10 to the power minus 4 at CCDF. This y-axis called as CCDF, complementary cumulative distribution functions, and this one is the called as PAPR, right? As you know that if we keep increasing, as this line shows graph, this line shows for the graph of for the number of subcarriers is 32. This line shows for the number of subcarriers 32, and this one is 64 and 128. We just keep increasing. We are just observing the different number of subcarriers. What has happened? The PAPR also increases, right? So this is all about some results that we have. And now this is the very important uh, topics. This is very important things that we are going to discuss. What is the effect of the high behavior? And also we are going to discuss in this slide how the behavior arises and why we are going to reduce the PPR. We will all going to discuss in this slide because it is very, as far as the OFDM system is concerned, is a very important parameters that we have to be considered. First, I am going to tell you how the PPR is, how the high PPR is occurring. You know about that many sub-carrier component during I-50 operation. Many sub-carrier components are in the same phase because of the same phase sub-carriers at the output of the I-50 operation. Added, those signals are added to each other. That means if you are calculating the cross correlation of that particular symbols, you will get non-zero value. If cross correlation, that means suppose we have two signals x of one samples that we have and another samples that we have. The cross correlation is y. These are the cross correlation, which is nothing but expectation of xy, right? If cross correlation is if cross correlation is non-zero, it does not equal to zero, what will happen? That means the xy, the samples does not maintain the 90-degree phase shift. That means they are destroying the orthogonality. Suddenly the peak's power is very much larger than the average power. So that OFDM is known to have a very high peak power ratio. And what is the effect? What is the effect on the system? You know about that. Every communication system. Suppose we have a communication system that is channels and the transmitter side. We have a transmitter and a receiver. We have receiver. There is a in the transmitter side there is a high power amplifier. A amplifier will be there, right? A amplifier will be there, a high power that is called as high power amplifier. The high power amplifier, right? If high power amplifier working in a non-linear region, suppose this high power amplifier is working on a non-linear region, and it would be a very costly, right? The price of the high power amplifier which is working on the linear region is much lower than the high power amplifier which is working on the non-linear region, right? And if high power amplifier which is working on the non-linear region, that means it distorts the signals. A amplifier which working on a non-linear region, it distorts the signals. That means we cannot get those signals that we have sent by the transmitter, right? And also, so what is the impact due to the high PAPR? Due to the high PAPR, the high power amplifier working on a non-linear region, and this system, the cost of this system will be very high, and it can be signal distorted. It can be signal distorted, right? So in order to, so what will happen? What is the high PAPR due to the high PAPR? As I told you, the signal will be distorted in the non-linear because of the non-linear region of the high power amplifier, and that provides the degradation of the bit error rate, right? So this is all about what will happen after, due to the high PAPR, what will happen? Signal will be distorted. That's why that can provide the degradation of the bit error rate, right? And also, and also one more things that I'm going to tell you, the efficiency of the high power amplifier. if the system is amplified that working on non-linear region, that means because of the OFDM system is used in the mobile terminals and the battery, we have to compromise of the battery of this mobile terminal because of the high power amplifier which is working on the non-linear region, right? Due to the non-linear region, we have to compromise in the battery, the power of the battery in the non-linear region. During the non-linear region of the high power amplifier. So that first of all, we have to be understand what is the PAPR and what is the impact on the PAPR and what is the effect on the system performance due to the high PAPR. So, so that I'm going to conclude these slides uh, due to the in order to reduce the interest, in order to reduce the cost of the system or make our system cheap and best, we need to suppress those PAPR so that we cannot be so that there is no need for the compromisation of the battery. There is no need for compromisation of the battery in the mobile terminals that has been used that has been used that is used in by the OFDM, right? So this is all about the effect and of the high PAPR in OFDM system, right? So based on this, I have some many publications and uh, due minimization of the PAPR. So the two paper is based on based on the reduction of the PAPR that we have, and two paper is already communicated, right? And we have three conference paper, right? So I'm going to so thank you so much for watching me, right? Thank you so much. I'm just giving you. So this is all about. So this is all about the conventional OFDM discussions. OFDM about sorry. This is all about the discussion of the conventional OFDM systems and some mathematical discussion that we have already discussed. Right. So thank you so much for having me here.